After studying this chapter, you will be able to explain hand valves and how they are used. You will be able to work with inlet and outlet pressure regulators. You will understand solenoid valve operation and uses. You will be able to troubleshoot hot gas bypass systems. You will recognize centrifugal chillers and their uses. And you will be able to work with heat pumps and reversing valves. Hand valves are installed to permit easy isolation of system parts. This makes it possible to perform many types of repairs without loss of refrigerant. Diaphragm-type hand valves are used for smaller copper tubes, while ball and globe valves are used for larger tubing. An arrow on the valve body indicates the direction of refrigerant flow. Hand valves can be used to isolate and evacuate portions of the system without loss of refrigerant. They are often used to permit easy changing of filter dryers. A crankcase pressure regulator is an outlet pressure regulator. Its primary purpose is to prevent excess pressure from entering the compressor. Excess suction pressure often occurs at startup or after a defrost cycle. High suction pressure causes high discharge pressure, and the compressor may cycle on the overloads. Short cycling causes loss of oil from the compressor crankcase and possible trip out on the oil pressure safety control. The CPR is adjusted by turning a screw located under the cover cap. When making adjustments, the low-pressure gauge should be installed on the gauge port. Most refrigeration CPRs are set to limit the leaving suction pressure to 18 or 20 pounds gauge. This means the pressure entering the compressor cannot exceed 18 or 20 pounds. The CPR provides the compressor time to get the suction pressure under control, or below 20 pounds. This non-adjustable head pressure control valve automatically maintains a minimum head pressure during cold ambience. When head pressure drops to the set point, the valve allows hot gas to bypass the condenser and go directly to the receiver. The valve will bypass enough hot gas to maintain the minimum head pressure. An evaporator pressure regulator is an inlet pressure regulator or holdback valve. Its primary purpose is to prevent evaporator pressure from falling below the valve's set point. It is used to prevent evaporator freeze-ups on 2 temperature systems and multiple evaporators. The EPR is fully adjustable and can be installed anywhere in the suction line. To adjust an EPR valve, remove the cap and turn the adjustment screw with the proper size hex wrench. A clockwise rotation increases the set limit. A pressure gauge should be attached to the core valve port to observe the effects of any adjustments. Make minor adjustments and allow time for the system to stabilize. A typical application for an EPR is to prevent evaporator freeze-up. For air conditioning, the EPR is set to keep the evaporator pressure from dropping below 45 pounds. That's with R22. The purpose of an EPR is to prevent evaporator pressure from dropping below the valve's set point. In this 2-temperature system, the freezer is the primary system and the dairy cooler is secondary. An EPR is required on the dairy cooler suction line and is set for 68 pounds gauge. The EPR prevents the dairy cooler from getting colder than 32 degrees. A check valve is required in the freezer suction line to prevent the dairy cooler vapor from entering the freezer, in other words, hot to cold. The system's pressure control is set to control the freezer. Multiplexed evaporators refer to a system having more than one evaporator. Each evaporator has its own EPR to permit individual temperature control. Any number of evaporators can be connected to a single compressor and individually controlled by EPRs. A multiplex compressor system overcomes problems associated with a single large compressor. Each compressor is cycled on and off as needed by individual pressure controls. If one compressor fails, the system continues to operate with the remaining compressors. Solenoid valves are either open or closed. When electricity is not flowing to the coil, the plunger is in the down position, blocking flow. The valve is closed. When electricity is flowing to the coil is energized and creates an electromagnetic field that lifts the plunger from its seat. The valve is open. The pump down cycle is popular because it solves many problems. At startup, the thermostat closes to energize the solenoid valve. Refrigerant flows to the evaporator and suction pressure rises until the pressure control starts the compressor. At shutdown, the thermostat opens and the solenoid valve closes to stop refrigerant flow. The compressor continues to run until the low pressure side is reduced to about 1 pound gauge. This removes all refrigerant and oil from the low pressure side of the system before shutdown. Hot gas bypass is a method of making a large system keep running when the heat load is reduced. Large systems must make provision for operating during reduced load conditions to maintain temperature and humidity control. A practical solution is to bypass a small portion of hot discharge gas directly into the low pressure side. Hot gas only bypasses when the suction pressure is reduced to the valve set point. This method places a false load on the evaporator to maintain minimum operation. Hot gas is often bypassed to the suction line downstream from the evaporator. This bypass gas must be desuperheated before entering the compressor. The desuperheating thermostatic expansion valve, or liquid injection valve, is used to supply enough liquid refrigerant to cool the bypass gas down to 10 to 20 degrees of superheat. This is a cutaway view of a 500-ton centrifugal chiller with 3 compression stages, or volutes. The proper level of liquid refrigerant in the evaporator is to just cover the water tubes. The amount of liquid necessary in R11 chillers amounts to about 3 pounds per ton of refrigeration. This is a cutaway view of a water-cooled chiller system with reciprocating type compressor. Water in the open loop travels from the condenser to the cooling tower to be cooled for reuse. The water is open to the atmosphere inside the cooling tower, hence its name. Water traveling to and from the air handler is called the closed loop. This chilled water travels to the cooling coil inside the air duct to absorb heat. This water loop is not open to the atmosphere and returns to the chiller evaporator to be recooled. A two-pipe chiller system may have one large air handler or individual air handlers located in different areas. The two-pipe system pumps cold chiller water in the summer and hot boiler water in the winter. Changeover normally occurs in early spring and late fall. Shut-off valves and check valves are used frequently. In the four-pipe chiller system, the air handling units are located in areas that require individual heating, cooling, or humidity control at all times. The heat pump is an air conditioning system capable of reversing the refrigerant flow to function as a heating source. When operating in the heating cycle, the outdoor coil becomes an evaporator instead of a condenser, and the indoor coil becomes a condenser instead of an evaporator. Thus, the outdoor coil absorbs heat from the ambient air and discharges this heat into the home via the indoor coil. The system thermostat controls the reversing valve coil, which determines the direction of refrigerant flow. The reversing valve coil may be energized during the cooling or heating mode, depending on the manufacturer. Movement of the piston is performed by system pressures controlled by the valve coil. As shown in the cutaway views, the restrictor meters refrigerant during the cooling mode, but allows unrestricted reverse flow in the heating mode. One control is needed at each coil, because when one control is bypassing, the other is metering. The need for expansion valves, check valves, bypasses, or capillary tubes are eliminated. This older heat pump system uses two thermostatic expansion valves and bypass lines with check valves. When one check valve is bypassing refrigerant around the thermostatic expansion valve, the other check valve prevents bypass. This illustration shows the cooling cycle only. A capillary tube will meter in either direction. A filter is normally placed at each entry to the capillary tube. Check valves and bypasses are not needed. The drawing shows the heating cycle only.